Hello everyone, let's talk about another easy problem on Leetcode today. Find if path exists in graph Leetcode 1971. It's an easy problem because we will jump into it why, but I think it's mainly dealing with graph traversals, and if you know that it's super easy. So it states that given a bidirectional graph with n vertices. So bidirectional means like if there is a h from u to v, then we also have h from v to u. It says that, so that means when we are traversing, we can easily go from U to V and V to U. So that doesn't matter. And where, so it says that where each vertex is labeled 0 to n minus 1 inclusive, and the edges are represented as a 2D graph, where a 2D array where edge I is equal to UI to VI. And that also means like VI to UI, right? Because that's what bidirectional graph means. We have to determine if there is path exists between source to vertex destination. So it says that like we have to just check if their path exists. We don't have to give path or anything. It just wants the path to be there. And we have to return true if the path exists, otherwise we will return false. So they have also given one example, two examples. So when n is equal to 3, so we have what you say vertices 0, 1 and 2, and then we have h from 0 to 1, right? We can see that here. Then 1 to 2 also is here, and 2 to 0 is also there. And then it says that source 0 and destination is 2. So in this case, what will happen is like we will return true because we can see there is a path existing. So either we can what you say go from 0 to 1 to 2, right? Or we can directly go to 0 to 2. So it does not matter if it's a short path or long path. It just means the path should exist. Similarly, in the second problem, like there are 6 edges from 0 to 6, right? 0, 1, 2, 3, 4, 4, 5. And there is a edge from 0 to 1 and 0 to 2. But then we have a disconnected graph. That is like there is an edge between 3 to 5, 5 to 4, and 4 to 3. But there is no edge between any of the what you say vertices in the different graph. Like for example, if 0 to like 1 to 3 was connected, then this then the graph would have been connected. But the idea is that there is and the source destination is source is 0 and destination is 5, so that means we can't reach from 0 to 5 at like at all, so, right? But if the input was 0 to 2, then actually the answer would have been true, or if it was 3 to 5, then the answer would have been true. So this is what this problem is. Now let's jump into the solution space, like how we can do that. So one of the easiest ways, like we can either do the depth first search or breadth first search. And if we are able to reach to that node from the starting node, that is the source node, then that means then we can just return true in that case. But if we finish the DFS or BFS from the starting node and we couldn't find the destination at all, that means the graph is not connected, and in that case we will return false. Another handy data structure we can use is union find data structure, or disjoint sets as they are called. So in that case, we can just say if parent of u or parent of v is equal to same, that means the graph is connected, and we will be able to reach out to the one point to another easily. But I will not be covering that in this video because I have to first cover what disjoint set means in a proper way, and then we can just reuse it here. But I'll definitely make the video on this later. Now let's jump into the example. Suppose we have a graph which has like 6 vertices in it, right? So we can say that, okay, we have vertex 0, right? 1, 2, and what you say 3, and then vertex 4, right? And we also suppose vertex 5, right? So, and this is how the connections look. And suppose our initial destination, initial source is 0 and destination is 4. And if we start a DFS, I think the idea is simple. We create a stack, add the value 0 to the stack, right? Also add 0 to the visited set, Then we go to the neighbors 1 and 2, add them to the stack. So now this, so first, then we pop out 0 from the stack, but now we have to process those neighbors, right? Of 0. So we will see if 1 or 2 are in the visited set or are they equal to destination. Then the answer is no. So we will just add them to the stack. So now our stack will be 1 and 2 in it, and in the visited set we will have 0, 1 and 2. Similarly, now we pop out 2 because that's at the top of the stack. So we will see who are the neighbors of 2, right? So it will be 3 and 0. So 0 is already visited, and 3 is not yet, what you say, processed or visited. So we will just add 3 to the stack and mark and just I think when we pop out, I think 2 is automatically marked as visited or processed. So not visited, sorry, processed. And now we have 3 at the top of the stack. So we pop out 3 from the stack, right? And now our current element is 3. We check who are the neighbors of 3. It's 1, 2, and 4. And 4 is one of the destinations, right? So, and 1 and 2 are already visited. So we will just, yeah, we will just return true in this case. But suppose if the source was 0 and destination was 5, in that case we will not reach 5 at all, and our stack will be empty and we will return false in this case. Now let's think about like the similar solution with the BFS. Um, like suppose we have the same graph, right? 0, 1, uh, sorry, 1, yeah, and 2, 4, 3, and finally 4 and 5, and again it's connected in the similar way. And suppose the initial source is 0 and destination is 4. Again we add 0 to the queue and to the visited set, right? Then we pull out or yeah, remove 0 from the queue, and now the neighbors are 1 and 2, right? So we will add them to the queue, right? And also to the visited set. So visited set becomes 0, 1 and 2, and sorry, 0, 1 and 2, and the queue becomes I think for some reason I'm having issues here, yeah. And q becomes 1 and 2. So we pull out again 1. We see who are the neighbors which are not yet visited, or are they equal to destination. In that case we will return true. But neither like 0 is already visited and 3 is not yet visited. So we will add 3 to the queue, right? And we will also add 3 to the visited set. So our visited set now becomes 0, 1, 2, and 3. Now we pull out 2 from the queue. So we see who are the neighbors of 2. Are they equal to destination? Answer: neither 0 nor 3 are equal to destination, nor they are in the and they are already in the visited set. So we don't have to add them to the queue. And we will add it. Then we will also remove now 2 from the queue, right? Uh, and now we come to 3. 3 has 2 neighbors, or actually 3 neighbors, 1, 2, and 4. 1 and 2 are already visited, and 4 is not yet visited, and also it's equal to destination. So we will just return true, uh, and uh, uh, and this is our answer. But I think suppose if source was 0 and again destination was 5, we wouldn't have reached it, and that would have been what you say, that would have returned false in any case, because our queue would have been empty and our BFS was complete, but we couldn't find the destination. Also, one thing, one mistake I made, just that's what I wanted to share also in this case, was the time complexity. I think it's E plus B, but it also depends on how aggressively you add what you say, nodes to the visited set. So for example, if I go with the same algorithm, like 0, like 1, 2, 3, and 4, right? So I'm just removing 5 because I'm just talking about time complexity bit now. So what we can also do is like and it's a valid BFS or DFS solution, is like I add 0 to the, let's talk about BFS. I'll also share the example as a demo later on. So suppose I added 0 to the queue, and I didn't add it to the visited sets, right? So suppose instead of adding it to the queue, I'm marking it as not visited, but I just mark it as visited when I actually process it. So then I pull out 0 from the queue, right? So initially queue was 0 and visited was empty. So I pull out 0 from the queue, add it to the visited set, and also at the destination, the neighbors, in this case 1 and 2, right, to the queue, right, but not to the visited. Now what will happen is like one of the neighbors will be of 1 and 2, both will be 3 and 0, but 0 is already visited luckily, but 3 is not yet, right? So in both the cases, till we process any of them, or till we will add 3 to the queue, but we will process it only once, because we are just caring about the visit set. So let's look at the example. So we now add 1 and 2 to the queue, but they are not yet visited. Sorry, I think, yeah, this is the visited set. So we only have 0 in the visited. Now we pop out 1. And who is the neighbor of 1? It is 3. So we will add 3 to the queue as well, right? And also 1 to the visited. Now we again pop out 2, right? But 2 is not yet visited because it's not, sorry, 3, and the neighbors of 2 are 0 and 3, right? 0 is already visited luckily, but 3 is not yet visited according to the processing part that we were talking about. So we will again add 3 to the queue. So you see, we are double processing the node if we are not adding the visited node into the set at the start itself, and that adds to the time complexity because we are duplicating the processing. Of course, there will not be any issues because once we pop out 3 from it and it's already visited, we don't have to, we add it to the visited set, right? So it will be 3 again. We go to the neighbors of it. It will be like an idempotent what you say operation, uh, and again we add 3 to the visited again when we pull out 3 again from here, but set already has visited, so there will be no problems at all. And again the neighbors of 3 will be again processed, which is like 4, 2 and 1, but 1 and 2 were already visited and 4 was not. So next time when the 3 is processed, 4 was already in the visited set, but we will again add 4 twice, right? So because 4 was added to the queue but not to the visited, right? So that's why the time complexity, or there will be a time limit exceeded. I will just also demonstrate that case as well. So be aware of this when we are doing it in the competitive programming. But both of them are valid BFS and DFS algorithms, just that they are slower. Uh, Now let's jump into the code. So, so the first thing we have to do is like we have to create what do you say, a graph, and we will be using the adjacency list representation. It also states that let's look at the constraint. So they are saying that there are no duplicate edges, there are no self edges, and what they are also saying is like the edge length will always be equal to 2 and ui is not equal to vi, that is the value will never match, so all the vertices are also unique from 0 to n minus 1. So in this case what we can do is then we can use a hash map as a set key set or the vertices set, and all the adjacency list will be the value in that set. So what we can do is like something like this. So this will be our graph. Now we will just be building this graph. So we will just loop from less than, I think before even doing this, one edge case I actually forgot. What if source is equal to destination? In that case, we don't even have to do DFS or BFS. We have just found the answer there itself. So in this case, we will just return true. Right? So that's how it should be. And Now, in other cases, we will just build the, what you say, graph now. So now what we have to do is like, if we will just add it to the graph, and so once we have created all the vertices in the node, vertices in the graph, we will just loop on the edges now. So we will just get the current. So, okay, let's do it this way. Int u is equal to edge 0, for example, and int v is equal to edge 1. Right now we have to just do is like graph.get u dot add v, right? And similarly we have to do the same thing for the reverse direction because it's a bidirectional graph. And now that we have it, we have built our graph and we are ready to start the DFS, for example. Now as it is a DFS, we will just create the stack. Sorry. Right, and similarly we will just create a visited set of integers. Also in stack we need to add the source. Right, and similarly we will add aggressively to the visited set as well. Now while the stack is not empty, we will just continue this operation. So first thing we will do is like we will get the current element from the stack, right? Dot pop and start looping onto the neighbors of the stack. So we will just say for in neighbor of graph dot get current, we will just check if neighbor is equal to destination, we will return true, right? Else if neighbor if visited dot contains neighbor, then we will just continue. Otherwise we will just add uh, current neighbor to stack, right? Dot push neighbor, and what we will also do is like we will also add it to the visited set. And once this is done, yeah, I think our loop is complete and we will just return false otherwise, and it should do it. Let's run the code. Awesome, and let's submit it now. Cool. So this is DFS for the solution. Now let's jump into the BFS part. Now let's convert this algorithm into BFS. I think we just need to use queue instead of stack. So we'll just do that. And in Java, the linked list is a implementation of queue. So we can just use that. We can also rename this variable. And instead of push, we will just use what you say add method, right? And we will just replace queue with the stack with the queue variable, right? Because we are just converting it to the BFS. I think rest of the algorithm will stay the same. So instead of pop, now we will just do poll. And yeah, that's it. And now we can just run this algorithm and see if it works, or if there are some compilation issues, we should just fix them. Awesome. So this seems to work. Let's submit the code. Awesome. Yeah, it was fast enough. But now let me show you the case that I promised earlier, where if we don't aggressively add the nodes to the nodes to the visited set, and add it only at the time of processing, this slows us down a bit. So for example, we have already seen the example. So instead of adding, I also did it for the DFS, but for some reason DFS still passed. So it was not very slow for the lead code standard. But with BFS, there was a problem because we are doing it in a wave. So there will be a lot of neighbors in the next wave, which will actually be repeated. And this is why we see the problem with BFS and not with the DFS. So let me make this code bad. So I will just remove, so instead of aggressively adding it, I will just edit when I'm just processing here. So I will just move visited. I will just add what you say, mm, like the current node to the visited set, because I'm just processing it instead of as soon as I'm seeing it. So now this slows us down a bit. So let's see if my algorithm is correct. So I'll just add queue to the source, add it to visit to the current. And yeah, rest of the code stays the same. So now I'll run it. So for the small graph, this should not be a problem. Until there is some compilation issue, luckily none. And now let's submit the code. Come on, give me time limit exceeded. Yeah, finally it gives. So with when the graph is big, like with 20,000 vertices, for example, or nodes, for example, then this kind of slowness becomes visible. I hope you like this video. I can just revert this now. So that yeah, this works. But yeah, and please share in comments if you want to see the union find solution faster, because that data structure actually is built for this kind of answer, like is there a path between two nodes A and B, or are they part of the same connected graph somehow. And this is what this joint set or the union find algorithm does for us. I hope you like the video. The code link is in the description. And have a nice time. Thank you.